Hello everyone and welcome to Control Engineering and Dynamical Systems tutorials. In this tutorial, we explain how to develop a state space model of a double mass spring damper system. We also explain how to simulate the derived state space model in Python. The main motivation for creating this video tutorial comes from the fact that mass spring damper systems are prototypical and generic systems that can represent and model a large number of physical systems and dynamical systems, such as car suspension systems, harmonic oscillators, robotic arms, etc. But before I start with the explanation, I kindly ask you to press the like and subscribe buttons. Thanks a lot! Okay, let's start. The system is shown over here. This system consists of two objects with masses of m1 and m2. The objects are connected by springs and dampers. Here is the spring and here is the damper. The damping constants of the first and second dampers are d1 and d2. Similarly, the spring constants of the first and second springs are k1 and k2. In the panel A of this figure, the system is shown in its equilibrium point without external inputs, that is, without external forces acting on the system. On the other hand, in the panel B that you can see over here, the force F is applied to the second object. Due to the action of this force, both objects are displaced from their equilibrium positions. The displacements from the equilibrium positions for the first and second objects are denoted by S1 and S2 respectively. In this video tutorial, the velocities of the first and second objects are denoted respectively by S1 dot and S2 dot. On the other hand, the accelerations of the first and second objects are denoted respectively by S1 double dot and S2 double dot. The main goal of this video tutorial is to develop a state space model of the system. For that purpose, we need to construct free body diagrams of object 1 and object 2. In the sequel, we will explain all the forces that you can see on these diagrams. Okay, let's start. X and Y are horizontal and vertical axes. Then I and j are the unit vectors of the x and y axes respectively. Then Fs1 is the force that the spring 1 shown over here is exerting on the object 1. This force is defined by this formula. In this formula, K1 is the spring constant, S1 is the displacement of the first object from its equilibrium point, and as we mentioned previously, I is the unit vector of the x-axis. Then this force, denoted by Fd1, is the force that the damper 1, shown over here, is exerting on the object 1. This force is given by this formula. In this formula, d1 is the damping constant, S1 dot is the velocity of the first object, and as mentioned previously, I is the unit vector. Then we have this force N1. This is the surface reaction force exerted on the object 1. And over here we assume that there is no friction between the objects and the surface. Consequently, we don't have friction forces. Then m1g is the weight of the first object. Over here, m1 is the mass of the first object, and g is the gravitational acceleration constant. Next, we have the force Fs21. This is the force that the second spring is exerting on the first object. The formula for this force is given over here. It's equal to K2, where K2 is the damping constant of the second spring, multiplying S2 minus S1. Over here, S2 is the displacement of the second object from its equilibrium point, and multiplying the unit vector I. Then we have this force denoted by Fd21. This is the force that the second damper is exerting on the first object. The formula for this force is given over here. d2 is the damping constant of the second damper. s2 dot is the velocity of the second object minus s1 dot, that is the velocity of the first object, multiplying the unit vector I. Similarly, the force Fs22 is the force that the spring 2 is exerting on the second object. Similarly, Fd22 is the force that the second damper is exerting on the second object. And we also have m2g, that's the weight of the second object, where m2 is the mass of the second object, n2 is the surface reaction force acting on the second object, and F is an external force applied to the second object. In this video tutorial, we neglect the masses of springs and dampers, and consequently we can establish these two equations. Let's analyze the first equation. This equation involves Fs21 and Fs22 forces. The equation is telling us that these two forces have equal magnitudes and opposite directions. Similarly, the second equation involves Fd21 and Fd22. This equation is telling us that these two forces have equal intensities and opposite directions. By using these two equations and by using this equation and this equation, we can get the formulas for Fs22 and Fd22. Next, let's apply the second Newton's law. This equation represents the second Newton's law for the first object. Over here, a1 is the acceleration of the first object, and in words, mass of the object times the acceleration vector of that object is equal to the sum of all the forces acting on that object. And keep in mind over here that we are approximating this object as a point mass. And on the right hand side we can see all the forces acting on this object. Similarly, this equation represents the second Newton's law for the second object. Mass of the second object times the acceleration of the second object is equal to the sum of all the forces acting on the second object. Okay, the next step is to project these two equations onto the x-axis. Next, by projecting the first and the second equation onto the x-axis and by using the previous expressions for all the forces, we obtain these two equations. These two equations can be written like this by just regrouping the terms. Let's analyze these equations. We can see that the external force F is only affecting the second equation. Next, let's introduce the state space variables. x1, state space variable, is equal to s1, that is equal to the position of the first object. Then x2 is equal to s1 dot, that is equal to the velocity of the first object. Then we have that x3 is equal to s2, that is the position of the second object, and x4 is equal to s2 dot, that is the velocity of the second object. Let's now substitute these state space variable inside of this equation. Our goal is to obtain a system of equations that will look like this. On the left hand side we will have x1 dot, x2 dot, x3 dot, and x4 dot. And on the right hand side we will obtain some expressions that should be in accordance with the system dynamics. Let's obtain the first equation. The first equation is super easy. Let's simply take the first derivative of x1. The first derivative of x1, and I will write it over here, x1 dot is actually equal to s1 dot. Now, by looking over here, we can see that s1 dot is actually equal to x2. And here's our first equation. This equation is given over here. What happens with the second equation? The second equation should be x2 dot should be equal to something. Right. Let's see what's happening over here. If we take the first derivative of x2, we will obtain s1 double dot. Perfect. However, from this equation, we can actually express s1 double dot like this. And then by substituting x1, x2, x3, and x4 for s1, s1 dot, s2, and s2 dot in this equation, we will obtain this equation. By using the same principle, we will obtain the third equation and the fourth equation. The fourth equation is obtained by using this equation over here and by using this substitution. And that's it. This is actually our state space model. Let's analyze the complete procedure. This is our system dynamics. These are two ordinary differential equations of the second order. They're of the second order because over here we can see the second derivative. As the result of this substitution, we've wrote these two equations as a system of four first-order differential equations. Next, let's divide this equation by m1 and let's divide this equation by m2. As the result, we transform this system in this form. Now, we can write this system of equations by using vectors and matrices. Let's do that. Here's how we can write this system. We can simply group the left-hand side inside of this vector. Then, on the right-hand side, we will obtain this matrix multiplying this vector and plus multiplying this vector that multiplies a scalar f. You can simply verify that this is actually the correct representation. How to do that? Well, if we multiply this row with this vector, we will simply obtain x2. Next, if you multiply this row by this vector, and you do that element-wise, you will actually obtain this expression. And similarly, you will obtain the third and the fourth equation by multiplying the corresponding rows of this matrix with this vector. This is our state equation. In addition to the state equation, we need to have an output equation. The output equation actually tells us which variable is observed. For example, over here, I will assume that there is a sensor that will measure the distance s1 of the first object. So I can assume it's a type of a distance sensor, for example, an infrared sensor that measures the position s1 of this object. Since s1 is actually equal to x1, we are observing this state variable. And consequently, my output equation will look like this. I will have 1, 0, 0, 0, and this will actually be equal to x1. So this is the output equation. Again, to summarize, the output equation tells us which state space variables are observed by sensors. Our state space equation and the output equation can be written compactly like this. And this is the classical state space representation. Over here, the vector x, and keep in mind that vectors are denoted by bold letters, is given over here. The input is given over here, the A matrix is given over here, the B matrix is given over here, and the C matrix is given over here. Our next goal is to simulate the state space model in Python. We will use two approaches for simulating the state space model in Python. The first approach is based on the discretization of the model by using the Backward Euler method. The second approach for simulating the state space model is based on the Python's control systems library. Here's the explanation of the first approach for simulating the state space model in Python. The idea is to discretize the model by using the backward Euler method and to transform the continuous time model into the discrete time model that can easily be simulated in Python. And here's the main idea. Our state space model in continuous time looks like this. X dot is equal to AX plus BU. Let us approximate this first derivative like this. In this equation, K is a discrete time instant that goes from 0, then 1, then 2, and it increases. H, that is this variable over here, is a discretization constant. For example, a very small number, 0.001, depending on how finely we want to approximate the dynamics. Then, x with the subscript k is actually equal to the state at the discrete time instant k times h. And that's the whole idea. Then, what do we do next? We approximate this x dot over here, that is, we substitute x dot by this variable, and as the result, we actually obtain the equation shown over here. What did we do over here? We substituted x dot, and we simply took the right hand side, and instead of x, we placed xk, and over here, instead of u, we placed uk minus 1. For simplicity, we assume that the discrete time index of the input is k minus 1. However, we can also assume that the discrete time index of the input is k, if we want. However, then, when simulating the system dynamics, we will have to start from k is equal to 1, and that's inconvenient for me. From this equation, we obtain this equation. What do we do over here? We multiply the equation by h, then we obtain this equation, then we take this entry and we put it on the left hand side, we put some entries on the right hand side, and we finally obtain this expression over here, where I minus h times a inverse is actually the inverse of I minus HA. This equation can be written compactly like this, where AD is now discrete time A and B is the discrete time B, and they are given by this equation. On the other hand, the output equation stays as it is. That is, we have that yk is equal to cxk. And that's it. That's the complete idea. Simple as that. Now, let's write a Python script that will implement this equation. Here's the Python script, and I will explain a line by line. First, we need to import the necessary libraries. We need NumPy, then we need the plotting library and the plotting function. Then from NumPy linear algebra, we need inverse, since we will be inverting some matrices. Next, we need to define our state space model. That is, we need to define our A, B, and C matrices. Here they are, A, B, and C. So let's define them. To define them, we use NumPy arrays. Here's the first row of the matrix A, and here's how we type it in Python. Here's the second row of the matrix A, and here's how we type it in Python. Third row, fourth row. Okay, that's our A. Let's define B. We define B row-wise again. First, second, third, fourth, first, second, third, fourth row of B, and that's it. And finally, we have the C matrix. C matrix is a simple row matrix, and here it is. Next, to simulate the dynamics, we need to define the initial state. And over here, assume that all the states are equal to 0. Next, I need to define the number of time samples used for the simulation. I assume 30,000 time samples, and then I need to define my discretization constant h. That is this constant over here. Here's how I define it. Over here, I need to define the input sequence. I will simulate a scaled step response of the system. That is, I will simply assume that the external force F acting on the system is always equal to 10 newtons for the time duration of the simulation, that is, for 30,000 time samples. Notice over here that I'm actually not simulating the system behavior for 30,000 seconds. I'm actually simulating for 30,000 multiplying by 0.001. Keep in mind that. Next, I need to define the discretized system matrices. They're defined over here. Here's AD, and here's how I define this matrix in Python. Note over here that inverse is actually imported over here from NumPy linear algebra. Keep in mind that this is the identity matrix, that is this matrix. Here's my BD, here's how I define it, and CD stays as C. That is the same as the continuous time C matrix. Next, we need to check the eigenvalues of our system. This is very important for verifying the stability of the system. And let's do that. That is, let's execute the code until here. And let's see the output. Okay, now I will check the eigenvalues of the matrix A. And note over here that A is in continuous time domain. Let's print the eigenvalues. Okay, here they are. We want to create a stable system. That is, all the eigenvalues should have negative real parts. And we can see that indeed all the eigenvalues of our continuous time system have negative real parts, as you can see over here. Good. Next, let's check the eigenvalues of the discretized matrix AD after backward Euler discretization. And let's print these eigenvalues and let's see them. For the discrete time system to be stable, all the eigenvalues of the discrete time matrix A have to lie inside of the unit circle in the complex domain, and you can easily verify that the eigenvalues are actually inside of the unit circle in the discrete time domain, which means that the discrete time system is stable. And it's often the case when you use backward Euler method that you will obtain a stable system. On the other hand, if you use the forward Euler method, you might get unstable systems. So that's why my advice is always to use the backward Euler method when discretizing the state space dynamics. Our next goal is to simulate the discretized model, that is, to simulate this equation. And here's the function I wrote that achieves this goal. This function accepts input arguments AM, BM, and CM. These matrices correspond to our AD, BD, and CD matrices. Then it accepts initial state, input sequence, and time steps. Then over here, I define two matrices. These matrices are used to store, number one, the state sequence, and number two, the output sequence. And then, in this for loop shown over here, I simply propagate this equation recursively in time. Let's explain that. The discretized model looks like this. xk is equal to AD xk minus 1 plus BD uk minus 1, and yk is equal to CD xk minus 1. Let's start from the time instant k is equal to 1. And what do we have from these two equations? We have x1 is AD x0 plus BD u0. Consequently, by knowing x0 and by knowing u0, we can compute x1. And then we can simply compute y0 as CD x0. And this is how we do it. Then, let's compute x2. x2 is equal to, according to this equation, AD x1 plus BD u1. Then, since we have computed x1 from this equation, we know x1 and we know the input, so we can compute x2. And similarly, we can compute y1 as CD times x1, and x1 is computed from the previous step. And this is how we do it. We just recursively propagate this equation in time to compute the complete state sequence, that is to compute x3, x4 until the end, let's say until xn. And that's exactly what is implemented over here. For example, over here you can see how I multiply am times x plus bm times u, and then I compute x, then I recursively do that over and over in time, and finally I return the xm and ym matrices, and keep in mind that xm and ym matrices are filled column-wise as this iteration is running. And that's it. Over here, I call the function, I specify the input matrices, the initial state, the input sequence and time, and finally I plot the results. So let's do that. Let's see the results. Okay, here it is. Let's see what we are plotting over here. I'm plotting actually the velocity of the first mass. If I want to plot the position of the first mass, I will simply type this, and let's see the output. Here it is. Here's the position of the first mass, or better to say the first object in time. Now, let's save the simulation data, since I will be using this simulation data to compare this approach with the second approach. I can do it like this. Let's erase everything, and let's clear the screen over here. Here's the second approach for simulating the dynamics. This approach relies upon Python control systems library. To install this library, you will simply open a command prompt and you will type pip install control. This is an amazing library that can be used for simulation and for control system design. Again, I need to import the necessary libraries. I import the plotting function, then I import my control systems library as CT, then I import NumPy. Over here I defined a simple plotting function that's used to plot my results. Here's the function. This function accepts time vector, response vector, title of the plot, x-axis label, y-axis label, and the string file name. That is, this function will actually save the plot in a specific file, and the extension of the file will be PNG. Okay, again, we need to define our state space model. Here's how we do that. The same procedure, then we define the initial state over here, and over here I'm using this function CT from the control systems library, and I call SS. Then I specify the input matrices A, B, C, and D, and this will define my state space model. For those of you who are familiar with MATLAB, this function is actually Python implementation of the SS MATLAB function for defining state space models. Let's define our state space model and let's print it out. Here it is. Here are the inputs, here are the outputs, and here are the states. Perfect. Next, let's simulate the step response of our system. I specify the start time, I specify the number of samples, I specify this discretization step, I specify the end time, and I define my time vector simply by using NumPy linspace. I specify the start time, the end time, and the number of samples. Next, I define the control input vector for simulation. Here's how I do it. And here you should keep in mind, since we will be comparing two simulations, that this scale factor for my control input is the same as in the case of the previous simulation. Let's verify that over here. Yes, it's the same. Perfect. Let's continue. To simulate the system, we use this function ct.forcedResponse. We specify the state space description defined over here. We specify the time vector. We specify the control input vector defined over here, and we specify the initial state. This function will actually solve ordinary differential equations, and it will simulate the system response. Let's do that, and let's analyze the returned output. Here's the returned output. It's actually a structure. This structure has the following variables, or better to say objects. If we want to access the simulation time, we will simply type return simulation.time. This will give us the simulation time. Then this output will actually give us the output of the system. The return simulation.state will give us the state matrix sequence, and here are the inputs that are used for simulation. Perfect. Let's now plot the results. And let's plot again, let's say, the position of the first object. Over here I'm calling the plotting function, I'm specifying time, I'm specifying the variable that I want to plot, title of the string, what I'm plotting on the x and y axis, and I specify the name of the file that will be saved. This function will actually save this file and it will plot the results. And let's see the output. Here it is. Here's the position of the first mass or the first object over time. Now, let's save the simulation data such that we can compare it. Cool. Now, over here in this script, I will compare two simulation results. I saved two files. This file actually contains the state sequence matrix obtained by simulating the system by using the control systems library, and this file contains the state sequence, or better to say the state sequence matrix obtained by simulating the dynamics by using the backward Euler method. But before I do that, let me just erase everything from my workspace, and I will clear my workspace. And let's load these variables. Here they are. Here's the state sequence obtained by using the control systems toolbox, and here's the state sequence obtained by using the backward Euler method. And let's plot the results. Over here I will plot, for example, the velocities of the first object, and I will compare two discretization approaches. And as you can see over here, the results are identical. Perfect. This means that my backward Euler discretization is actually comparable to the control systems library implementation. Okay, that would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.